Okay, so Unit 5, system modeling, and these are the learning outcomes. So the first one is have a thorough understanding of how graphical models can be used to represent software systems and how to apply several types of models to represent a full system. Apply and evaluate the fundamental system modeling perspectives of context, interaction, structure, and behavior. Apply unified modeling. Ability to develop and evaluate executable systems developed using model-driven engineering, and to further classify them as either structural or behavioral models. So let me just take you through an introduction. So you should be asking yourself this question. The topic is system modeling. What is a model? Okay, so a model is a representation. Okay, it's a graphical representation of something that exists in the real world. We find models not only in software engineering, but also in construction. Before they can build a house, obviously they have to know the specifications of the house. They model the house. Okay, so it gives the developers a visual representation of how the final product should look like. It adds a higher layer of abstraction. So in the previous lecture, we covered requirements engineering. So this systems modeling is we refer to it as a higher layer of abstraction, where now you're taking the requirements that you gathered, okay, and you're doing an analysis. Remember that although it's tempting to think that modeling is done at the design phase, it's actually part of the requirements analysis phase, not the design phase of the SDLC. Because the design phase of the SDLC, what you are actually doing now is you are designing the actual components of the system. So you take the diagram of the database, which you would have done during requirement analysis, and you're now producing it on a database management system. You're taking the drawings of the UI and you're actually creating them on an IDE. Okay. So that's what modeling is. And we do it during the we do requirement elicitation. After requirement elicitation, then we do modeling. So your models and your requirements that you just gathered all form part of that specification document. And we said that you have to be able to use natural language specifications so that when you give these specifications and models to people that are not technical, they're able to interpret the system the way a developer would. Okay, so which brings me to the next point. Systems modeling is defined as a process of developing abstract models of a system, with each model representing a different view or perspective of that system. So there are there are different models that we can draw when we're modeling a system, and these models were each invented to show a different perspective. Okay, so we're going to talk about these different perspectives during the lecture. Systems modeling uses unified, we refer to it as unified modeling language, okay, which uses graphical representations. All of these models, or these diagrams that we're going to talk about today, they are referred to as UML. So if you're asking an exam or a test, use a UML diagram to model the requirements given in a case study. UML are represented by these diagrams that we're going to talk about, graphical representations. During the design stage, models are used as form of deriving detailed requirements, which were discovered during the requirements engineering process. So during the requirements engineering process, you would have specified during you discovered the requirements during your elicitation process. And then we use those designs or these models in the design stage of the SDLC. Okay, so we said systems modeling defined as a process of developing abstract models of a system. Models can be developed from different perspectives, and these are the perspectives that I was talking about. So we have the external perspective, we have the interactive perspective, we have the structural perspective, and then we have the behavioral perspective. So what's the difference between these different views, okay? So the models that are categorized as external perspective, they show how the system, okay, exists and is related with other subsystems, okay? So it shows you, external perspective shows you the environments at which the system is running in, what platform is it hosted on, and which other systems is it operating with related systems. Then we talk about interactive diagrams, okay? So interactions between systems and its environment, or even between the components of a system are modeled. So interactive diagrams show the different role players, the actors, which events they trigger on the system, how it shows how the actors interact with the system, okay? And then we have what we call the structural perspective. The structural perspective speaks to the data. So what kind of data structures are we storing in our database? And the ERD is a good example of a structural, we refer to it as a structural diagram because it shows the structure of the database. Then we also have behavioral perspective. And with the behavioral perspective, it's more concerned with the different states that a system can be in, and also speaks to dynamic behavior. What kind of messages are the different subsystems sending each other? So for the purpose of today's lecture, we're going to stick to one example to represent all these different perspectives, okay? And we're going to make reference to an ATM, right? Most of you should know what an ATM is, but for those of you who don't, an ATM, abbreviated as ATM, automatic teller machine, or we can refer to it as the automatic banking machine, is a banking subsystem that provides bank customers with access to financial transactions in a public space without the need for a cashier or clerk or bank teller. So customers can go to that particular bank ATM and check their balances, check their accounts, they can deposit funds, they can withdraw funds, they can transfer funds. And all of this, what I've noted here in the second point, we can refer to it as use cases. Remember, we spoke about use cases in the previous lecture. We said these are use cases of functions on a system. That's how you define a use case. So a use case diagram would be something that consists of multiple use cases. And I'm going to show you an example of how a use case diagram would look like for an ATM. Okay, so we're going to stick with this example of the ATM for consistency purposes. And then they go on to say, ATM technician provides maintenance and repairs. All these use cases also involve bank actor, whether it is related to the customer transactions or to the ATM servicing. So from here onwards, they're talking about now the actors, okay, or the stakeholders in terms of what we know about requirements gathering. there would also be stakeholders in the requirements engineering process. So they later on become actors in terms of the UML diagrams. So in your test or exam, you may be given a problem domain similar to this, because this problem domain that's in front of us now, it obviously doesn't talk about a problem, but it gives us a perspective of how things work in the banking industry. Okay, who are the actors? What are some of the use cases that are normally triggered on the system? So you could be asked to, you could be given such an extract similar to this, and then you asked, can you produce a use case diagram for us? Can you produce an ERD or a domain class diagram for us? Okay. So moving on to the first example. So this is how a typical context diagram would look like. Now, a context diagram is an example of an external perspective because it shows the system along with all other subsystems that it has to interact with. If we think about the bank's ATM system, okay, there are other subsystems that you just see the ATM, okay, and you think, okay, this machine is doing everything, but in the background, the ATM itself is divided into other subsystems. The accounting database, that database that all of this information is stored on, is stored on a different subsystem, a different database management system, and that database management system has the account information of the customer. Okay, then we have the system that dispenses the cash. Okay, that's in charge of detecting whether it's giving you the correct notes. Then we have the system that prints out any warnings, or if we don't have money or whatever, it prints out some stuff. Okay, and then we have the system that's in charge of displaying this stuff to you. Let me just find a laser here. Okay, so then you have the subsystem that displays the information to you. Then you have the subsystem that reads your card. Okay, then you have the subsystem that controls the keypad. Then you have the control system, okay, which controls the commands and how the commands are, such as your SQL and so forth, the SQL code. So you can tell from this context diagram which other external systems interact with this ATM system. So that's a critical example of, I think you guys would have done something similar to this in doc analysis in your second year, the context diagram. Then we have the interactive perspective, okay? And this is the use case diagram. This is what a typical use case diagram looks like. This rectangular block here, we refer to that as the automation boundary, okay? This is the automation boundary, and the automation boundary represents the system itself, okay? As you can see here, you have to label it the bank ATM system. So this is the automation boundary, which represents the system. All of these oval shapes inside, they represent the use cases. Okay, so this is a use case diagram. It's not a use case, it's a use case diagram. Don't confuse the two terms, okay? So what are some of the use cases for an ATM? Customer will check its balances, deposit funds, withdraw cash, transfer funds. There's going to be some sort of maintenance happening, and there's going to be some sort of repair. Okay, so we have the automation boundary, we have the use cases, we also have the actors. Okay, now normally human actors are represented by stick figures, as you can see here. Then we have institutions also as actors, which can be represented as, like, as you can see, the bank here as a building. Okay, but the primary thing that you need to take out of this is that there's always going to be is always going to be an internal actor and an external actor for a system. In this particular case, we're talking about a bank. So the bank itself, the people, the administrators and so forth, the people that work at the bank, they will be the internal actor of the system because they're in charge of the administrative tasks. Then we also have the external actors, which is your customers and the people that service the ATM. Okay. Now, when you have a use case diagram with multiple use cases, it is important to link up the use cases with the correct actor, because the customer won't trigger all of these use cases themselves. Okay, so you need to link the correct actor to the correct use case. You can see from this particular system that the only use cases that will be triggered by this actor is checking who their balances, depositing funds, withdrawing cash, and transferring funds. Then we have someone who refills the ATM, for example, the people who refill the ATM. They're going to be doing any maintenance, repairs. Okay. Then the bank may be one of the actors which triggers most of them, if not all. So it's important to show that don't just draw the automation boundary with its use cases and then draw the actors on the outside without linking them to the correct use cases. That's very important. So this is what we mean by showing the interactive perspective. So when you're talking about the structural perspective, we refer to it as the data structures, okay? And we are trying to understand the relationship between these different data entities. Just like how you did in your assignment with the learning system. Here is another example with the typical banking system and the structural. It just consists of examples of some entities you normally find. Okay, this is a domain class diagram. We need to get used to using that term instead of ERD. Why is it a class diagram? It's a class diagram because, unlike how we did it in the previous years, we're not only now showing attributes, but we're also showing the different functions that are triggered by that particular entity. So in this example here, this is a class diagram that shows a relationship of generalization and specification. If we go from bottom to top, we refer to that as a generalization relationship, okay? If we go from top to bottom, we refer to that as a specialization relationship. So as you can see from this structural perspective, it's showing us more on the side of the hierarchy and the inheritance, as opposed to the different links or the number of links between these entities. So it's not showing one-to-one, one-to-many. It's showing the inheritance. It says that regardless of whether it's a savings account or a check account, it's going to have, or it's going to inherit a bank account number from the superclass. We refer to this as the superclass, and these become subclasses, or also parent class and child classes. So the child classes or the subclasses will always inherit their attributes from the superclass. So it doesn't matter whether it's a savings account or checking account. It will have a bank account number. It will allow the person to withdraw an amount, deposit amount, and transfer, and so forth. Okay, so that's how we show this structural perspective, by showing the relationships or the inheritance between the different data structures. So in the next slide, you're given a description of this class diagram. So class diagram defines the type of objects in the system. and the different types of relationships that exist among them. It gives a high-level view of an application. This modeling method can run with almost all object-oriented methods. A class can refer to another class. A class can have its object or may inherit from other classes. Okay, so just like the example I showed you in the previous slide, that a class can inherit its attributes, okay, from other classes. So essential elements of UML class diagrams, you would have typically the name of the class, the attributes, and its operations, just like how they did here. It's going to be the name of the class, the attributes associated with the class, and all the methods. In programming, we refer to them as methods, okay, or operations or functions that are triggered by this particular class or entity. And then we also have the behavioral perspective, which a good example of the behavioral perspective is what we call the system sequence diagram. Okay, now the system sequence diagram shows multiple things. Okay, the first one is it shows you what are the various subsystems similar to the context diagram. It also shows you the different messages that are being sent. Okay, so all the different variables that are being sent between these different subsystems. Okay, in some cases they also include an actor here in the front of the system sequence diagram, but in this example they didn't. So sometimes it also shows you the actor. So what does this mean? Okay, oh yeah, there is represented as a subsystem as well. They refer to it as the user. So we have the user here. So how does this work? So the user in the system sequence diagram, the user will insert their card. When they insert their card, it triggers an action on a different, or it triggers a behavioral change on a different system, which is the ATM system. And what will happen is that the ATM will then request a PIN from the user. The user will enter a PIN, and then the ATM now has to go to a different subsystem, which is usually maybe the accounting system or the database that resides at the bank or on the bank server. So the ATM now has to go to a different subsystem to verify whether the PIN that was entered by the user is correct. If it's incorrect, then it's going to terminate everything, okay? And then it's going to start from scratch. If it is correct, it's valid, then it's going to go and process that. And it's also going to send you options of things you can do on the ATM. Goes back to the user, okay? Now, the user clicks on a particular option and they click on, for example, withdraw, okay? Now the ATM would request an amount back from the user that they want to withdraw. So this usually is represented by a dotted line, but this blue part, we refer to them as we refer to it as a lifeline, okay? And the lifeline basically represents a particular task in execution, okay? So this is the system sequence diagram. It shows the different subsystems and the messages that are sent between the different subsystems. So these are the common mistakes that people make when drawing system sequence diagrams. Designers tend to make these common mistakes. By avoiding these mistakes, you can ensure that the quality of your diagram. Adding too much detail. Remember, you can even go on the internet yourself and search system sequence diagrams. These things can look very complex. The example I showed you now, this is a very basic form. I didn't even include, there's no other addition, there's other notation that should be in here, which maybe if you look in the study guide or you look at various examples, you see that notation. You can use loops notation here so that if a particular condition is not satisfied, then the system will do a loop back. Okay, so there's different other components that make up the SSD. So don't add too much of detail, unnecessary detail. It clusters up the diagram and makes it difficult to read. Obsolete and out-of-date system sequence diagrams that are irrelevant when compared to the interfaces, actual architectures of the system. Don't forget to replace them or modify them, okay? So certain notation on the system sequence diagram is no longer in use. So you need to make sure that you are familiar with the latest UML specifications for system sequence diagrams. Leaving no blank space between the use case text and the message arrow. This makes it difficult for anyone to read the diagram, okay? So don't leave unnecessary spaces in your messages, okay? Because remember, these messages here can be interpreted as functions also, or methods rather. So insert card can be sent with other messages, usually in a more detailed use case diagram. We're able to put a bracket here and say, okay, when the person inserts the card, it has information that it's sending to the ATM, such as maybe the customer's name and surname and so forth, okay? So in a more detailed use case diagram, you get to see that. So don't leave blanks between use case text and the message arrow, not considering the origins of message arrows carefully as well. So another example of a behavioral perspective is the state machine diagram. So we have the SSD, system sequence diagram. Then we also have the state machine diagram, and it does just that. It shows you the different states that the ATM can be in. You know, from those of you would have interacted with the ATM. Okay, we start here. Wherever you see this solid dot with an arrow, that's where we normally start when interpreting these diagrams. So with the state machine diagram, we're going to start here. When you first walking towards an ATM, the first state that it's going to be in, if there's nobody using it, it's going to be in an idle state. Okay? So an ATM can take these three forms. It can be idle, active, or out of service. So when you first walk to the ATM and you start interacting with it, it's going to be idle. What needs to be done for the ATM to go from idle state to active state? Okay, the user needs to insert their card. So when the user walks up to the ATM and it's idle and they insert their card, it takes the ATM from an idle state to an active state. Now it's the ATM is responding to you, okay, as the user. What needs to happen for the ATM to go from idle state from active state back to idle state? Either the user cancels the transaction or the user is done withdrawing, depositing, or transferring cash, okay? Then for the ATM to go from idle to out of service, what needs to happen? Well, there has to be somebody servicing it, okay? Usually when the ATM is out of service, maybe they're refilling the cash. So for it to go from idle to out of service, there has to be some service in progress. For the ATM to go from out of service back to idle state, they need to have been finished with what they are doing. So they need to be finished fixing the ATM if there was any issues with it, okay? So this is a typical behavioral perspective because it shows you the different states that a particular system can be in. So state machine diagrams are also called state charts diagrams. State chart diagrams are used to capture the behavior of a system. UML state machine diagrams can be used to model the behavior of a class, a subsystem, a package, or even the entire system. It is also called a state chart or a state transition diagram. So from what we've spoken about, we now know that models can be data-driven. They can also be event-driven. So when we're talking about data-driven modeling, show the sequence of actions involved in processing inputs data and generating associated outputs. Event-driven modeling, these types of models show how a system responds to external and internal events. So events-driven modeling speaks to features or functions, and then the data-driven one speaks to inputs and outputs of data. Then we also have model-driven engineering. Models, the principal output after the development process, and it is the approach to requirement engineering. The next concept that we're going to talk about is model-driven architecture. So what is model-driven architecture? Model-driven architecture is an approach to IT system specification that separates the specification of the actual functionality from the specification of the implementation, okay? And this helps to reduce the amount of errors. It speeds up the development time. It also, most importantly, it ensures that you implement reusable, independent application models, okay? So you're able to implement reusable platform independent models. So these are the 3 layers of abstraction that are found as part of the model-driven architecture. We have the computation independent model, we have the platform independent model, and then we have the platform specific model, okay? I'll just show you this next slide so that you can have a graphical representation of what this actually means. So if you're speaking about the computational independent model, we are saying that it represents the layer of abstraction that speaks to the problem domain. So understanding the domain that we're doing the system for or building the system for. If it's a hospital, we know that the domain has particular entities. So we refer to that as computational independence model because in that layer of abstraction, we're not really concerned about what or which platform the features are going to be implemented on. We're just concerned about the features themselves, okay? So computational independence modeling, which is done at the requirements gathering. When you're gathering the requirements from the problem domain, you're not really speaking about which platform you're going to solve this issue with, okay? It's independent. It's the layer of abstraction requirements gathering. It happens at the requirements gathering, and it's independent of the platform, okay? If we go a layer higher during the analysis phase, okay, we now do a platform independent model where we take these requirements here that we gathered here, and we draw these use case diagrams, system sequence diagrams, state machine diagrams, and so forth. As you saw yourself from those models, they don't speak to anything about a platform. So at this level of abstraction, okay, it's platform independence. It is platform independence. However, once we've gathered the functionalities of the system and we have the different drawings of the models that we've done during the requirements analysis, we can now start to design specifically for a particular platform, which brings us to the next layer of abstraction, which is referred to as platform-specific modeling. Okay, so what platform-specific modeling means is that in the previous steps, you didn't care about anything regarding a platform. You just gathered the functions, designed, done the models. Now we're going to be producing this system for either Java, C#, or whatever, HTML. So now it matters for us. It actually matters that we become platform specific, okay? Because the way you design a system on Java the way you design a system, whether you're building it on an Android for Android mobile devices or you're building it for iOS or whatever, it's going to be different because the UI components are different. So there is a need to be more now platform specific. But here's a benefit of putting in these different model-driven architectural abstraction layers, is that we can take these layers here. We can take these layers and still reuse them on a different project. Okay, maybe we were initially building a Android app. Now we want to move to iOS. Doesn't matter. We can take these two layers of abstraction and then become platform specific and design for that particular platform. So that's the beauty of it. Using model-driven architecture is that you separate your functionality. You separate the functionality of the system from the implementation, how it's going to be implemented. If you see here, it shows some of the benefits rather of using model-driven architecture as opposed to the classical way of how things were done. Okay, now in the classical method, the people that are working in the project have to be experts of everything. Okay, they have to be application developers, they have to be platform experts. Okay, all in one. You have to know all the different platforms, and you have to know the domain as well. Be a domain expert, be an expert at understanding the business and the problems that face the business as well. Okay, so this one here was very unsustainable, but now with model-driven architecture, we're able to have separation of duties. So we're able to gather a team, and each person in that particular team is an expert at a particular component. So we have people that are experts at the domain that we're building the system for. So they understand how, for example, sticking to the hospital, they understand how a hospital operates. So they are the domain experts. They know the different entities and so forth. They're able to give us advice on that. Then we have people that are experts at different platforms. So they're able to tell us, no, guys, in terms of Linux, this is how you want to implement the system. In terms of Windows, this is how you implement it. Then we have people that actually write the code, the developers, okay? So here we have some sort of separation of duties, and it's more efficient. So in conclusion to that, we said that a model is an abstract representation of the real world, and models are needed to represent or design a system. There are several types of models which are described in this unit, and these are context, interaction, structural, and behavioral models. Context models show an overview of the whole system, and context diagrams are used to represent the context models. Interaction models, action between user and the system, okay? And lastly, use case diagrams and sequence diagrams are examples of interaction models, okay? So that's a wrap, and that's study unit 5 in essence, talking about systems modeling, okay? So are there any questions for you guys? Because we're not going to see each other on Friday, so do you have any questions? And giving you time to ask any questions in general, doesn't have to be pertaining to today's lecture. Okay then, so I guess